Okay, let's get started. So welcome everyone. My name is Benjamin, and I'm really happy that you're all showing up to come and listen to the announcement or the introduction to what we're offering with Columnar storage. As I said during the little cameo in the keynote, I'm Belgian. I'm not really into social media style exaggerations, but I am super excited that we're finally able to talk to you about this and give this to you, because it is available today as part of the developer preview for 22.2. And why is it so exciting? Because it's just a wonderful feature that as a technologist I'm super excited about, but also this has been a long time in the making. It's actually the last global summit, 2019 in Boston. The day after the summit, there was a kind of a gathering of some of the engineers in the SQL group and the kernel group, where we, for the first time, kind of started seriously planning for this project. So it's that long that we've been working on it. Well, I should say that only a couple months later, the actual development started in the kernel group, 2021. The SQL team also got engaged because we really built this from the kernel up till the SQL level. So here we are with 10 times faster analytical queries. 10 times may sound a little arbitrary or a little bit marketing-y, but it's kind of an analogy because it's an order of magnitude. So if you like running, try running 10 times faster. If you like driving a car, try driving it 10 times faster. If you like flying a plane, like Scott, try flying it 10 times faster. It really requires different thinking, different technology, and in the case of transportation, a different vehicle to go 10 times faster. Even though sometimes it may sound like trivial in the world of IT, it really is a very significant step. The important thing to remember here is that with InterSystems Iris, the vehicle stays the same. It is the same engine. It's just the engine that we've taught to work with columnar storage. Okay, let's talk. I carry the clicker around and I never use it, but anyway, I will. So I'll first talk a little bit about the motivations, why we went on this journey. Then I'll talk a little more about the architecture, how we built it, what's in the box, and I'm not talking about that box here. And then I'll talk a little bit about some of the advantages, some of the things that we kind of got for free thanks to InterSystems Iris. And then it's time to kind of continue the demo that we started earlier on the main stage, and just make it 10 times faster. Okay, I mentioned we'd start by talking a little more about the problem before talking about the solution. So let's do that first. I'll start from very high-level descriptions, but these translate into really fundamental technical patterns or paradigms. So most of our customers today are using InterSystems Iris for application scenarios. We've got many customers in various industries. So they could be in healthcare, an application such as an electronic health record system. We have customers in financial services that process transactions. There's an ATM network that runs on InterSystems. We've got customers in retail, such as what Gert was presenting earlier today. So really all across the spectrum. And what all these applications have in common is the way how they go about the data, how they go about the records in that data set. So if you're in HR, you look up one patient based on its patient ID that might be in a barcode on a wristband, and you look up their medications. If you're in a financial services setting, you open your app and you see the most recent transactions for your account, also looked up based on your ID. Also, when you're making a transaction, when you're kind of wiring some money to a friend or whatever, you're updating one row based on the information from, or you're subtracting a certain amount from one account and you're adding it to the other account. That's your transaction. And you want that to happen in an asset, in a consistent way, so that the money doesn't get lost in between. So those are typical application scenarios, and this is what InterSystems Iris has supported for decades in a very efficient manner. And when you're working with data in this, and these applications may also update things. Sorry. So in the relational world, in the SQL world, you would talk about rows, you're inserting rows, and you're trying to insert them as fast as you can within the context of your transactions. And you're inserting, updating, and fetching them kind of one or a handful at a time. And when we're retrieving them, we're also typically retrieving them based on a very specific criteria. For example, looking up the patient by its ID, checking for the most recent transactions based on the account ID. So queries are using very specific criteria. You're getting back the full row, so all of the medication information for that patient, all of the details of a transaction to visualize in the app, etc. So focus on full rows, very selective conditions, and the focus for Iris to support these transactions is on latency. You want to make sure that you retrieve the patient's medications or allergies as quickly as possible, because if you're late, that's bad. If you're trying to withdraw $100 from your account from an ATM, you want that to happen within a couple seconds at worst, because it's too late, that's bad. If you're queuing up at a till in Spar, you don't want to have to wait 5 minutes before you get your check. So all of these scenarios require that you are able to access those rows in a very quick fashion. So you want to store your data in the way that it's used. Yes, you can remind me later that you want to update. So the focus is on latency, and it doesn't work at all anymore. There we go. So we're going to store data how it's used, row by row. That's the natural thing to do. In analytics, the world is very different. The type of usage patterns are very different. For example, you might be doing some population health analysis, writing a big query that scans across 100,000 patients at a time. In financial services, you might do a valuation exercise of your portfolio, kind of matching your current positions with the latest price information that you get from your market database. In retail, maybe you're analyzing the evolution of purchases, of sales throughout the year, correlating it to the weather. So these analytical queries, these analytical use cases have very different characteristics. You are also selecting data based on criteria, but like in the example here, these are criteria that are much less specific. They are much more generic. For example, you're looking at all of the sales data for a whole year. You're looking at all of the patients that have diabetes, which could still be 30% of your population. So the way how you're interacting with that data is very different. Also, you're not necessarily interested in getting back row-level data. You want aggregates, you want a sum, you want a count, you want a standard deviation, you want to find correlations. So that it's a very different way of acting on your data. So in the relational world, you would be talking about complex queries, large tables with where you're doing aggregations and no longer are interested in the individual records. For example, if you're doing that sales analysis, in one query you're interested in grouping by region and not interested in product lines or categories at all, so you want to ignore that. And then in the next query is the inverse. You're only interested in the product categories and the whole hierarchy, and the region doesn't matter for you. So you're much more selective in a vertical way. The users of these systems also have different expectations. If you're doing the quarterly report, if it takes a couple seconds, that's not too bad. You're only running that query once per quarter. Obviously, you want it to return in an efficient way, but that efficient is very different from the minimal latency requirement that we had in the application scenario. So it doesn't really hurt if these queries take a little longer, but you know that there's a lot of work in them. There's a lot of compute happening, which means that you would like it to be efficient. I was just in a meeting with a customer who once again was expressing the importance of having important costing details or resource utilization that you could attribute to your queries. So especially if you're running in the cloud where you're paying per CPU second, it is very important that your system is efficient. So the focus is going to be on throughput in this scenario. Now, this is where our earlier row-by-row storage model, where we're storing physically the data in a row model, is not such a good fit anymore. So if I need to do a single I/O operation for all 100,000 of the patients that I'm selecting with my query, and then extract the information for the columns that I need in the particular aggregate that I'm doing, that's not a very efficient model. Let's consider one of the most powerful Iris deployments that we're aware of from our friends at Epic. They have a mighty system that consists of a huge data server with 23 application servers, 23 compute nodes, that all added together reaches 88 million global references per second. With that system, they're able to serve up 40,000 power users on a single system, 40,000 concurrent power users on a single system. That is massive. That is super. That's super effective, and they've optimized their application for that use case, and the application is interacting with the data in kind of a row-by-row fashion, individual patient records, individual pieces of information for that patient. But if you only have 88 million rows that you can scan per second, and you need to scan a billion row table, that takes 10 seconds. So that's 10 seconds that this whole super mighty cluster is busy working on one query across a 1 billion row table. We'll be doing some demos with a 1 billion row table later on. This is not super scientific, this little description, but I hope it kind of gives you the message comes across that if you're storing your data by rows, that you're at some point going to be very constrained by I/O, and your CPUs are going to sit idle while they're waiting for all of that data to be read from disk. So those were challenges that we were seeing when we were competing against dedicated analytical databases at some of the customers that we've interacted with in the past 5 years. We were typically able to kind of make up for a row storage model by using by investing in compute nodes and leveraging ECP, which is really powerful. We could kind of scale out horizontally on the data tier as well using our sharding, and we really did reasonably good. But eventually, at the end of the day, the efficiency of the system was kind of constrained by the having to do 1 gref for every row that eventually your result set is going to touch. Okay, so what we want to do for analytics is store the data how it's used column by column. If we're only querying by region in our sales table, then I don't need to read the product column. And if I'm operating on something, if I'm aggregating the sales amount, then I want to be able to operate on that column at a time and not first have to extract it, et cetera, et cetera. So we needed to store data in a columnar way because that's how it's used, and that's how it needs to be stored, and that's how it needs to be operated on. With that, let's take a closer look at what we did and how we built this. So as kind of a warm-up or appetizer, I first wanted to talk a little bit about bitmap indices, which I guess many of you are already using. Who's using bitmap indices already? Great, perfect. It is a really efficient design, and it really focuses on the same kind of constraints that I was just talking about, but only solving the problem at the index level. So let's take a closer look at how a bitmap index works. For many of you, this will be very familiar. So on the left-hand side, you see a regular index. So where you're based on a field value, you can find the corresponding IDs on the second subscript. This is very efficient because it means that you can, if you're looking up based on a particular field value, you're immediately finding all of the corresponding rows. So if you're going in by patient ID, you'll immediately find that one record for that particular patient. If you're looking at like a 3-year database and you have you need to look up by month, then probably there's going to be a ton of data for every month. So for fields with a low selectivity that are not so specific as an identifier, this model or these indices might become a little big and unwieldy. But still, they're very practical for an application scenario. If you delete a row, you have to delete one index entry, and you're not impacting anything else in your database or in your index. The bitmap index, on the other hand, is actually encoding the IDs in a dedicated data type, $bit, which is string-based, but it's still you could call it a separate data type. So we're kind of packing our information for multiple rows and we're putting it in a single I/O. So with a single I/O, you're getting data for, in this case, 64,000 different records. So that is very efficient for those kind of low selectivity things that we've seen in the analytics scenario. So just a little more about $bit. So $bit is that dedicated string-based data type that was designed specifically for this purpose, giving you a kind of an encoded format that can tell you for 64,000 rows at a time whether they're a match or whether they're not a match. The beauty of bitmap indices is not that it has some optimizations both in the storage and the compute area. So this is sorry, I'm kind of getting ahead of myself a little bit. So we're looking at how it's used in bitmap indices, and now we're looking at that right-hand side of the global, the value part of the global, the $bit data type. So how is $bit itself optimized on storage? So it's a dedicated data type for just Booleans, 0, false, or true. And it uses an internal structure that's fairly flexible. So if you only have a few values in there, it will use some sort of an internal list structure. If you have repeating values, it will use some sort of a run length encoding version. So it enables a very tightly packed information that is much more efficient than 64,000 ones and zeros if you would store it in a simple string. We obviously experimented quite a bit, but not intended. And we found out that 64,000 was actually a very practical way, because how your bitmaps or your bit strings ended up was very practical to work with a default 8K block size. There's also optimizations on the compute side. Maybe you're familiar with the bit count and the bit find and the bit logic operations. Those are implemented as kernel functions that are made really efficient, that allow you to take advantage of fast paths at the compiler level, and they enable these to be very efficient for example, when you're combining different bitmap indices and need to find the intersection or the union of two sets of conditions. Also, because our primary audience has always been in application scenarios, we made sure that you could do atomic updates. So remember in the previous chart here, if you're making an update to a row and you need to update the corresponding index value for a regular index, that's not really complicated, because there's only one node that you need to touch. If you're updating a row for which there is a bitmap index defined, then you need to make an update to a value that is shared with 64,000 minus 1 other rows. So you have to be a little more careful there. But we implemented those atomic updates at the kernel level as well, so that they could be made efficient. We made sure that they're also compatible with ECP and journaling. So with that, we have a mechanism for indices that kind of addresses the analytical needs that I was talking about. However, that's still the indices. So, and it doesn't help with the aggregates that I was talking about earlier. And it also is kind of secondary storage. Once you've found the list of IDs, you would still have to go to the full rows to find out. So the next level beyond bitmap indices, beyond these kind of column-oriented or analytics-oriented indices, is the columnar storage for the primary data structure, which is the master map, which is our table data. So at a logical level, we have a simple table with a set of columns. On Iris, you may know that, or you will probably know that it is stored in globals under the hood, but we don't really need to know the physical layout in order to interact with the table. That's the contract of SQL. And if you want to know more about that, I have a session about the SQL optimizer later on. And we want to keep it that way. So we want to just work underneath this logical level so that users shouldn't have to care about how their data is actually laid out on disk. So the current default physical storage is row-oriented, which means that we'll have a master map stored in a global where, indexed by row ID, we store the row data in list format. List is a very efficient format for covering data, grouping data of various data types. And it really aligns well with what I was talking about earlier with those application use cases. In the columnar model, so this is the new thing that we're introducing today. We're storing things differently. So we're now storing it column by column. And if you're interested, there's a nice video that went live today, produced by Online Learning, which has a much better animation than what I'm capable of in PowerPoint. But we're storing data column by column. So here you can see a separate global for every column. Again, we're chunking it in chunks of 64,000 values, but I didn't have enough room on the slide to make that visible. And now there's a couple of different things that you can see, because you know that so that first column there was a string, so I can store it in a new data type that we call vector. More about that soon. And so we've got all those strings in there. We've got all those integers in the next column, and we've got all those decimals in the next one. So we've kind of transposed our $list data, and now have it stored in separate globals per column. Let's recap on what we're actually optimizing this for. So what is the goal that we wanna achieve? So earlier on, I was talking about latency. So the goal of row storage is to make sure that you have the lowest latency for your transactions that operate on individual rows. So we're clustering our data, we're grouping our data points, so the individual field values, for point IO access by row. We've kind of packed them, we've encoded them using $lists for dynamic access. So I don't need to know all of the different data types up front. I can just keep appending to them, and I can access them through objects or SQL, however I would like. I'm also caching all the fields for a few rows. So my cache is also grouping the data or looking at the data by row. Just about that packing, the flexibility. So one of the consequences of using $list is that you will pay a little for that flexibility. You pay a little bit of unpacking overhead price when you're accessing field values from, say, the far end of the list. But that's okay, because we're only talking about a handful of rows, because we're in the application world where you're only working with a handful of rows at a time. And that doesn't weigh up against the flexibility that we're winning. With columnar storage, we're aiming for something different. We're aiming for throughput. We're aiming we're grouping the data by column so that you can get the data for 64,000 values at a time. And we also know the data type, and that is what we can exploit in the way how we encode the data. So that's the $vector thing you saw earlier. And again, we can optimize for throughput, for making sure that we know, or we can have a quicker access path, because we don't have variable length content in these vectors. Also, we cache the fields that we need for a query, and we don't cache all of the fields that we're not interested in. Again, going back to that example about the query on the sales database, if one time I'm gonna do a report based on geography, I'm not interested in the product dimensions or some of those other dimensions, so they don't pollute my cache. If I'm in a row scenario, I inevitably will be reading and caching full rows. So again, this is a focus on throughput, a focus on efficiency. So a little more on that encoding piece. So we're introducing a new data type, a new language feature, an internal data type that is focused on storing large arrays, 64,000 values, of values of the same data type. And also typical for analytical data is that there might be, you might have a lot of columns, and you might have a lot of nulls in those columns. So what we're doing with $vector is also optimizing for sparsity. Under the hood, within $vector, we're going to identify regions of sparse or dense data, and we'll dynamically switch between them, storing the dense data in kind of an array-like structure, and storing the sparse data using a run length encoding to be really efficient. We can also exploit the data type. So I mentioned that unlike $list, there's going to be quick access paths because you know the length of what you're talking about. That sounds like at odds with being able to store strings, but that isn't, because we use dictionary encoding for strings. So we store a small dictionary of all of the string values that are in your chunk, in your vector, and then we can just, the actual data is then becomes an integer ID, a key into that small dictionary that's also inside your data type. And we're adaptively scaling up and down for integers. If you have an integer that can be expressed with 2 bytes, we're only going to be using 2 bytes for your dense regions. And of course, we still intend to support applications, so we also implemented atomic and bulk update support. So even if you're using ECP, mirroring, journaling, if you update one value in a vector, we will not store the whole vector for 64,000 values in your journal files. We'll store only the atomic update, which allows us to also offer transactions on columnar organized data. So that's the optimizations that we're putting in on the storage side. If you would only optimize on the storage side, but still operate in a row-based model and iterate through all of those values in your columns row by row, then you wouldn't be winning as much. You would be taking advantage of the cache localities, etc., but there's still much more to be gained. And in fact, you could say that we were kind of lazy, because we're actually taking advantage of a lot of stuff that actually is out there. We didn't have to reinvent some of the efficiency wheels that are out there. So it turns out that modern CPUs love tight loops. So loops where you have only just a very small, simple operation that's inside your loop. A CPU can recognize that, can chew through billions of rows or billions of values, iterations for such a loop in a second. Also closely aligned with that, SIMD is our chipset level instructions. SIMD stands for single instruction, multiple data. So those are chipset instructions where you're operating on multiple data elements in one go. So rather than put one value in your register, put another value in the next register, and then summing those up, you can put 4 values in the first register, 4 values in the second register, and then summing those up pairwise with a single chipset instruction. So those are advances that are now becoming mainstream in CPUs that are very interesting for these kinds of bulk operations that we're looking for here. And then the best part of it is that we don't have to hand code those instructions. Compilers are smart enough to recognize an opportunity for SIMD and will automatically convert your code to use those low-level instructions. So there's advances on the compiler end as well that we're able to take advantage of. I don't want to kind of play down all of the hard work that was put in by our kernel developers, but they were able to take advantage of a lot of things that are now out there and that can help us operate in a columnar fashion. Also, because we were storing data or because we were encoding data in specific ways, we can exploit that encoding. For example, if you have sparse data, you don't need to go through your sparse data in a loop like this. You don't need to go through the whole logical range of your 64,000 values. If the data is very sparse and you only have a couple of run length blocks, you can just look at those. You can just loop through those blocks and calculate your results in that way. When you have dictionary encoding, you first look up in the dictionary which indices you need to operate on, and then it becomes an integer operation, which is a lot cheaper to execute. So these are all kind of very low-level things that we were exploiting in order to support fast vectorized processing. And we implemented, similar to the IDs in the $bit world, we implemented through $vector operations. So how does this look on Iris? We've implemented these dedicated internal functions that exploit tight loops. They're full of tight loops. They're auto-vectorized by the compilers that we're using. We're exploiting SIMD instructions because of that. We're exploiting our run length encoding. We're exploiting our dictionary encoding. So that's what those dollar vector functions are capable of. Which functions did we implement? Well, everything that SQL needed. So we've been very pragmatic in that set, as you will find out if you download the kit. This is an internal set of functions that is currently not available for direct use by customers. It's only part of the generated code for your SQL queries. But once we get the hang of it, and when we ditch the experimental label, we may well publish that for users to take advantage of. Anyhow, how does it look? So here's an example of a little bit of vectorized execution. So in this little code snippet, I'm ordering through a global that has vector data. So we call that our first column. And then I'm using a vector operation on it where I'm producing a filter a bit string, because it's very closely aligned with our bit string. So this is producing a bit string that has true values for all of the elements inside my vector column 1 that are equal to ABC. You can imagine how this looks with a dictionary encoding. You first look up in the dictionary whether ABC is there, and if ABC is there, you figure it out with the array of dictionary indices. And then we're using that filter as a mask for a sum on a second column. So this is going to be a numeric vector that has some other value, and we're applying a filter on that. So I made it a little more complicated by adding that bitmap filter or that bitstring filter here, but that is also key to how these SIMD operations work. These SIMD operations are not blunt and only able to support full sums, but you can kind of refine them by passing in these sort of bitstring filters. So this kind of code is exactly what you'll see in C being used by SQL. So again, if we would have stuck to just storing things in a columnar way, we wouldn't have been able to get to that 10x improvement. So you'll see that our SQL query plans are now full of vectorized processing, full of that kind of code where you're operating on a chunk at a time. It's only at the very last moment, until we really can't postpone it any longer, that we're going to reassemble rows, and only those column values that are actually needed to get the query. So we're postponing the slow train, we're postponing the row operations until the very last moment in query processing. Also interesting is that the fact that everything happens in chunks, everything happens in these 64,000 blocks of rows, means that, or gives us a nice platform to implement parallel execution. For those familiar with the matter, up to now, SQL queries that parallelize will generate a parallel subquery that looks at partitions of the data. So it kind of, every query results in a new subquery, whereas with adaptive parallel execution, we're able to co-generate that into the parent query. That's a very technical or a very specific thing that maybe deserves an entire presentation by itself. But it is it's a really great opportunity within this columnar model to start operating in that chunk model, and we're going to roll this out to the rest of SQL processing in future versions, because it saves us a bit of a detour that we currently have to take. And again, I've already mentioned it earlier, calling ourselves a little lazy, which is not true, of course, but we're working through this model where we're using vectorized processing on the SQL level, taking advantage of dedicated operations or dedicated functions that we implement in the kernel that then are compiled into optimized code that leverages these SIMD instructions. We're kind of taking advantage of a whole array of optimizations. We can optimize on the SQL code generation side. We can optimize the kernel operations. We can look if our compiler has specific flags to make better use of SIMD on more recent chipsets. So we now are able to kind of scale up our performance optimizations across multiple fronts at the same time. So that's how the vector operations work. So we talked about optimizing the storage side, using that new data type, and optimizing the compute by a set of dedicated operations to work with that data type, and then kind of take that through our entire SQL processing model. Now, I mentioned that we had a couple of interesting advantages that are a consequence of this, or that we get for free after all this focus on performance. And first and foremost are the storage savings. I kind of gave it away a little bit when I was talking about the dollar vector data type. All of those encodings of sparse and dense regions and the data type specific encodings, they result in a much smaller storage footprint for data that gets stored in that way. So I mentioned that we're using that those sparse regions can offer really great advantages. The adaptive scale for integers is kind of a small thing, but especially if you combine that with the dictionary encodings for strings, then suddenly if you have say if you have a column with I would say yes and no columns, but yes and no are short strings. But if you have like a small set of values that are reasonably long strings, but if you first encode them using a dictionary, and suddenly it becomes an integer between 0 and 8 or between 0 and 7, then you can dynamically encode that in a single byte dense region. I'm getting really technical here, but those are very, very significant savings, and you don't have to do anything for it. We'll do it for you, and we'll change it dynamically if you add a 9th element, and we need to scale back to 2-byte integers. A couple of examples. So mileage varies. So we're not making your data 10 times smaller, unfortunately. We would like to look into that more, but here's a couple of examples of data sets that we've processed. So for example, the 40 million version of the New York taxi data set that I was talking about this morning takes 3.1 gigabyte in columnar layout and almost 6 without indices in the row layout. But if you want to do any kind of querying on it, you have to add indices to it. So it quickly gets into 6.5, 6.6 gigabytes. For one customer's data, well, this is how it looked. And then this last one is also interesting. That was a wholly optimized OLAP-specific schema. And you can see that the gains that we made there were really, really significant because all of those indices that were part of that schema. But again, mileage varies, and it depends on whether your data has a lot of random values or whether there are some patterns in there. So it's very hard to predict this. But I want to call out one example. So in the New York taxi data set, there is a yes-no column. That yes-no column is kind of for 95% of the rows, there is a yes or a no. And then for the remaining 5%, there's nulls. So we get some benefits from sparsity. So when I measured this in row layouts, I first loaded the data without that column and then measured how big my globals were. Then I added the column and I measured again. And I ended up with 120 megabytes for just that column. So that's 3 bytes per row. That makes sense because you got 1 or 2 bytes for the Y or the N, and then another byte that kind of encodes in dollar lists the length and the type of the next element. Now, when we were looking at the entire global, so not just the increment, but the entire subscript and value side, we ended up with only 5.3 megabytes. So that's 0.15 bytes for every row worth of data. So this is what you get with that encoding, with that adaptive integer scaling, with the dictionary encoding. So that's very powerful. But again, mileage varies. Not everything shrinks in the same way as our simple yes/no column. But you can think of data that's a very good fit, and data that's a slightly less good fit for it. So storage savings, great benefits. Mileage will vary, but I haven't ever found a data set where the columnar version took more space than the row version. The second thing I would like to point out is perhaps the more interesting one. So our SQL engine was built, I don't know, Aviel, you got to help me. Was it 20 years ago or 30 years ago? When you started working on the SQL engine? 25 years ago. 35. Okay, so a long time ago, we started working on the SQL engine. But at that point, we already had an installed customer base of hundreds, if not thousands, of big databases that had data that was using globals, that was using creative global structures where data was likely stored in a row-like fashion. Maybe it was using dollar lists, maybe it was using $piece to encode row values, and probably they also had index structures to quickly find patient records based on some kind of an index structure. And our intent with our SQL engine was to be able to project that existing data to SQL. So from the get-go, our SQL engine was designed with a very abstract, creative concept for the master map and index maps. And that is something that we were able to take advantage of when implementing columnar storage. We only have very little work actually to kind of make it supported conceptually. Of course, there's a lot of work in kind of ironing out the code generation, etc. But our SQL engine has always been familiar with the idea of different storage IDs or storage models. So you would say that was good for you. Why did it still take you 2 years? Well, okay. But what's in it for me? Well, what's in it for you is the flexibility that this gives us. I already mentioned that we're still using the same engine. So you don't have to install anything else. There's no limitations on the different on tables that you might be able to combine in a single query. There are very few vendors out there that offer you this flexibility. There's only 1 or 2 that actually have an integrated engine for row and columnar storage. Most others have 2 separate engines. Single store is previously known as MemSQL. Their name implies that it's the same, but they're 2 totally separate engines with limitations on how you can combine the data from those. That is not the case with Iris. With Iris, you can have a table that has a full columnar row layout, but you can also add a columnar index on a row layout table, which can be efficient to serve particular aggregations in an efficient way without forsaking the application-friendly row layout. We can combine row and columnar layouts in a single table. And one industry expert we spoke to was very enthused by this because he saw some opportunities for data that could benefit from the compact representation in a columnar form, but would also still need to see a lot of row materialization for some of the queries. I'm running low on time, so I need to accelerate a little bit, which is perfect because we're going to go to see a demo. Okay, I'll rush through this somewhat more quickly than I was intending, but at the Tech Exchange we can see some more of it. And Tom Woodfin, who has also been a core member of this team from the get-go 2.5 years ago, he has some more magic in stock at the Tech Exchange. So I mentioned that I would continue where we left off this morning. So just to recap, what we were seeing this morning is how we were looking at runtime plan choice, new part of our adaptive SQL optimizer. So if I'm doing a query on a table, I'm forced to use the default plan, and then you don't see it. Of course, I should have figured that out. How about now? Okay, so there we go. So this is with my default plan, and you've already seen this morning that we can do a lot better. We can make it how much faster was it? 6 times faster in this case. You also see that there was already a lot less I/O. And then with columnar storage, oh, my cache died. No, I just didn't click. Okay, you'll see that it suddenly got 11 times faster than the 6 times faster that we were seeing before. So this is all multiplicative. And also, if you see how many bytes were actually read, it's 72 times less than what we had earlier. So how does a query plan look in a situation like this? So I mentioned we're doing vectorized processing. So you'll see a lot of this, and this is, again, very dense, but I hope you like that. We're working in chunks. We're iterating over bitmap chunks, looking at vector chunks, applying vector operations. So this is how these query plans look, and we'll make them prettier in 22.3. There's another project queued up for that. But this is how we operate on those chunks as a whole. Now we're not done yet. We have a vectorized joiner function at the kernel level, and we are in the process of implementing that, of leveraging that at the SQL level. But you can already combine row and columnar layout, something that many of those other vendors aren't capable of. And if you do that on the row layout, it takes, for my 24 million row table, it takes about 10 seconds. But I can already do these kinds of queries with columnar storage as well, already 7 times faster when we're only able to kind of offer you a vectorized plan for everything just up to the join level. So in this plan, you'll see how we'll use partly vectorized processing and partly row processing. I didn't need you to read through all of that, but anyway. Sorry.
Did you flash your cache between the queries?
I have not, but I can show you. So the problem is if I don't flush my cache, it's the row ones are suffering badly, and if I do first a row query, my cache is full of rows, and then my columnar query is impacted by it. So I should run all the row queries first, and then all the column queries to have a more fair comparison.
It depends on the cache size.
But yes, it depends on the cache size. But when we're doing queries with 1 billion rows, you'll see that it's 200 gigabytes worth of data that you need for your row queries. So that is the economies just don't work out. Here's an example. So these are time travel rides where you arrived at an earlier time than you were dropped off. No, yes. And that takes 5 seconds in the row layout and 0.3 in the other layout. And these are some examples that really are the bread and butter of columnar storage. So here, if I do this on the row layout and then on the columnar layout, you'll see that we're making it 55 times faster. And then we'll end with a really simple aggregate. So that was quick on my row layout table. And now when I do it on columnar, oh no, I'm slower. What happened here? So, and the reason for this is that the row layout in this case, so let's look at the query that I was doing. I was doing a sum of passenger count, but my passenger count had a bitmap index on it. So our SQL optimizer noticed that and knows that that bitmap index has everything we need to satisfy this query. So it was already able to do a SIMD operation because our bit logic, our bit count operations are already on SIMD. So I had one vectorized SIMD query plan competing against another vectorized SIMD plan. So that's why it was in the same order of magnitude. So if we switch to a column for which we do not have that, then you'll see the power of columnar once again. So that was 126 times faster. So I got a couple more of these on a 1 billion row data set, which I don't have time for now. We're already a little bit over time. I'm sorry about that. We can walk through these later. I'll publish them on GitHub as well. But if there's any questions, you can certainly ask and then grab one of these Scrabble games for good questions. So
I have a question.
Please.
I understand that the column size is actually rotating the table by 90 degrees.
Mm-hmm.
So tell me if I understood correct. So the new layout is actually storing the data as multiple globals, which
yes.
Each of them are like acting like an index.
Yes.
Like a bitmap index, right?
Yep.
So actually the save on storage we seen before, it's because usually on most of the cases where you are talking about 1 or 2 columns indices, and I'm not talking about the classes that I have, I maintain 10 or 15 keys on an index,
mm-hmm.
I would save them, correct?
Yes, so a lot of the queries can be satisfied in an index like...
question number 2 is it correct that as more high value of scalability that I have on a certain column, it would be better for this new storage, correct?
If I have
higher scalability on data on a specific column. So
if
the scalability is very high, like the yes/no you gave on the taxi,
mm-hmm.
it will be very effective.
Yes,
but
absolutely.
if the scalability is very low, it means that you have like millions of different values. Then it will be less
Yes,
less effective.
That is true, and it's a good point because I forgot to mention it because I was already running.
The
over.
last one is because we have many globals as columns on the table, and actually I assume that you have a keyword in the class to say to the class compiler to use a different storage than the one that we know now. What would be the connectivity between that or the relationship to actually store each of the globals in a different database so we can map them across different machines or different disks on the same machine to increase the I/O? You have something like that, or we have to go manually back to the namespace global mapping and start mapping those specifics?
Right now you would have to do it manually, but it is actually a really great idea to, because we're looking into more capabilities for horizontal partitioning of your table data, but it's a good idea to also think ahead about that vertical partitioning scenario.
All right, thanks.
Okay.
So, we don't have to change so on this, we don't have to change our tables or anything?
We can't magically turn your row table into a columnar table. That's going to be what we call a table conversion. And in 22.3, we'll have a command for that, an alter table command that transforms your data. But right now, you would have to create a table using create table as select, and then just at the end, you append with storage type equals columnar, which is also how you create them. Create table with storage type equals columnar. So the conversion thing is something that we're still working on. But it's for the rest of your operations, everything is the same. All queries look exactly the same. Queries don't realize that they're hitting a columnar table.
Okay.
Until they finish 10 times faster.
All right. Okay.
We have seen that using leg space is faster, is more efficient. Is there a good reason not to use only columnar instead of the old storage? What's the drawback? I mean, there are some disadvantages.
Because it's not a good fit for application for small transactions. If the weight of your workload is more application-like, you're going to pay a price because you need to update. If your table has 10 columns, you'll need to update 10 vectors if you insert a new row. So there is we try to minimize that. We have a lot of good stuff in there already for this purpose, but there's a price that you pay at ingestion. I'm sorry I ran over this much, but sorry, that's passion, isn't it? But I'll be at the Tech Exchange and happy to answer your questions. But thank you.